So here's something to think about as you settle in tonight. Right now, as you're lying there, getting comfortable, letting the day fall away, there are objects out in the universe so massive, so ancient, and so deeply strange that they've been giving astrophysicists genuine headaches for decades. Not the kind of headaches you get from a long day. The kind you get when the math you trust, the physics you've spent your career building, tells you that something shouldn't exist. And then you point a telescope at the sky and there it is anyway. I'm talking about the oldest black holes in the universe. The ones that formed so early, so impossibly early after the Big Bang, that by all rights, they shouldn't have had time to grow as large as they did. And yet, they're out there, real as anything. Some of them billions of times the mass of our sun, blazing with the light of entire galaxies. And they were already that big when the universe was barely a toddler. We're going to talk about them tonight. Slowly, carefully, without rushing. Because the story of how we found them, how we've tried to explain them, and what they tell us about the earliest moments of everything is one of the most fascinating puzzles in all of science. And I think you'll find it's a surprisingly good thing to drift off to. Let's start at the very beginning. Not the beginning of black holes, the beginning of everything. Because to understand why these ancient monsters are so confusing, you need to understand what the universe was like when they were born. So, the Big Bang, about 13.8 billion years ago. Now, you've probably heard the phrase 1,000 times, and maybe you've got some mental image of an explosion, debris flying outward, the whole dramatic scene. But here's the thing. It wasn't really an explosion in any way you'd recognize. There was no space for it to explode into. There was no outside. The Big Bang was the rapid expansion of space itself, everywhere, all at once. Every point in the universe was the center, because the expansion was happening at every point simultaneously. It's a strange idea, and honestly, it's okay if it doesn't sit perfectly comfortably in your mind. It doesn't sit perfectly comfortably in most physicists' minds either. But the evidence for it is overwhelming. The cosmic microwave background radiation, the observed expansion of galaxies, the abundance of light elements like hydrogen and helium. It all checks out. Now, in the very first moments after the Big Bang, and I mean the first fractions of a second, the universe was unimaginably hot and dense. We're talking temperatures in the trillions of degrees. At that point, matter as we know it didn't really exist. You had this seething plasma of quarks and gluons, fundamental particles smashing into each other with so much energy that nothing stable could form. No atoms, no molecules, certainly no stars. Just raw, screaming energy and subatomic chaos. But the universe was expanding, and as it expanded, it cooled. Think about what happens when you let air rush out of a compressed tire. It cools down as it expands. Same basic principle, scaled up to the size of everything. And as the universe cooled, things started to happen. Within the first few minutes, literally minutes, protons and neutrons began sticking together to form the nuclei of the simplest elements, hydrogen mostly, a good amount of helium, trace amounts of lithium. That's it. That's the entire periodic table for the first few 100 million years. No carbon, no oxygen, no iron, no silicon, just hydrogen and helium, drifting in an expanding, cooling cosmos. And here's what matters for our story. For roughly the first 380,000 years, the universe was opaque. It was so hot and dense that photons, particles of light, couldn't travel any meaningful distance without slamming into a free electron and getting scattered in a random direction. Imagine trying to see through a thick fog, except the fog is made of plasma, and it fills the entire universe. Nothing could shine through it. There was light everywhere, but you couldn't see anything, if that makes sense. Then, around 380,000 years after the Big Bang, something beautiful happened. The universe cooled enough, down to about 3,000 degrees Kelvin, that electrons could finally be captured by atomic nuclei. Hydrogen atoms formed, helium atoms formed, and suddenly, for the first time, the universe became transparent. Photons were free to travel in straight lines, streaming across space unimpeded. That moment, that transition, is what we call recombination, and the light released during that era is still traveling today. We detect it as the cosmic microwave background, that faint, almost perfectly uniform glow that comes from every direction in the sky. It's the oldest light we can see, the baby picture of the universe. But after recombination, something else happened. Or rather, something didn't happen. For a while, nothing much happened at all. The universe entered a period that astronomers sometimes call the cosmic dark ages. No stars, no galaxies, no sources of visible light, just vast, slowly expanding clouds of hydrogen and helium gas, cooling further, drifting in the dark. If you could somehow go back and float in space during that era, you would see nothing. Absolute darkness in every direction. The cosmic microwave background would still be there, but by then it would have already red-shifted out of the visible spectrum, stretching into infrared and microwave wavelengths as the universe expanded. So to your eyes, nothing. Just dark. And this is where it starts getting really interesting, because somewhere in that darkness, something began to stir. Those vast clouds of hydrogen and helium weren't perfectly uniform. They had tiny, tiny density variations, slight regions where the gas was just a little bit denser than average. We're talking about differences on the order of 1 part in 100,000. Incredibly subtle. But gravity is patient. Gravity doesn't care how small the difference is. If one region is slightly denser than its surroundings, it pulls in a little more gas. That makes it denser still, which means it pulls in even more gas, and so on. This process, gravitational collapse, is how the first structures in the universe began to form. But here's what's crucial. It takes time. Gravity works at the speed of light at most, and in practice, the gravitational collapse of a gas cloud is a slow, gentle process. The gas has to cool. It has to lose energy. It has to settle into denser and denser configurations. And in the early universe, cooling was hard because there were no heavy elements. See, in the universe today, gas clouds cool efficiently because they contain things like carbon and oxygen, which are really good at radiating away energy. An atom of carbon can absorb kinetic energy from a collision, get excited to a higher energy state, and then emit a photon carrying that energy away. That's how gas cools, by radiating. But in the early universe, you didn't have carbon or oxygen. You had hydrogen and helium, and molecular hydrogen in particular, which is a much less efficient coolant. So the gas could only cool slowly, which meant it could only collapse slowly, which meant the first objects to form were big, really big. The first stars, what astronomers call population 3 stars, are thought to have formed maybe 100 to 200 million years after the Big Bang, give or take. And because the gas could only cool to relatively high temperatures before collapsing, these first stars were likely enormous. We're talking maybe tens of times the mass of our sun, possibly hundreds of times. Some theoretical models suggest individual stars of 300, 500, even 1,000 solar masses. Now, we've never directly observed a population 3 star, they would have burned through their fuel incredibly quickly, living fast and dying young, probably within just a few million years. But their existence is predicted by our best models of how gas behaves under those primordial conditions, and when those first massive stars died, they died violently. A star that massive doesn't just fade away. When it exhausts its nuclear fuel, its core collapses in on itself, and depending on the mass, one of two things happens. If the core is below a certain threshold, you get a neutron star, an incredibly dense ball of neutrons, maybe 20 kilometers across, packing more mass than our sun into a space the size of a city. But if the core is above that threshold, roughly 3 solar masses, give or take, then nothing can stop the collapse. Not the pressure of neutrons packed shoulder to shoulder, not any known force in physics. The core just keeps falling inward, crushing itself into a smaller and smaller volume until it forms a singularity, a point of, in theory, infinite density, surrounded by an event horizon from which nothing, not even light, can escape. A black hole. So the first black holes in the universe were probably born from the deaths of the first stars. And if those first stars were as massive as we think, hundreds of solar masses, then the black holes they left behind might have been pretty hefty too. Maybe 10, 50, 100 solar masses. Respectable. Impressive even. But here's the problem, and this is the thing that keeps astrophysicists up at night. The reason we're here talking about this tonight. When we look out into the distant universe, and remember, looking far away in space means looking back in time, because light takes time to travel. We see black holes that existed when the universe was less than 1 billion years old. Some of them less than 700 million years old. And these black holes aren't 100 solar masses. They're not 1,000 solar masses. They're 1 billion solar masses. Some of them are 10 billion solar masses. They're supermassive black holes, the kind that sit at the centers of galaxies today, and they were already supermassive when the universe was in its infancy. Think about what that means. You start with a black hole that's maybe 100 times the mass of the sun, born from the death of one of the first stars, and somehow, in less than 1 billion years, which sounds like a long time, but is actually a very short time in cosmic terms, that black hole has to grow by a factor of 10 million or more. It has to swallow the equivalent of millions upon millions of suns worth of material. And there are real physical limits on how fast a black hole can eat. This is the puzzle. This is the thing that doesn't add up. And the story of how astronomers discovered these impossible objects and how theorists have been scrambling to explain them is one of the great detective stories in modern science. It involves some of the most powerful telescopes ever built, some of the most creative theoretical physics of the last few decades, and a series of discoveries that have genuinely shaken our understanding of how the universe assembled itself. The first clue came from objects called quasars, and quasars have their own wild story, because when they were first discovered in the early 1960s, nobody had any idea what they were. The name itself, quasar, is short for quasi-stellar radio source, which is basically astronomer speak for, it looks like a star on a photograph, and it's blasting out radio waves, and we have absolutely no idea what it is. The man who helped crack the mystery was a Dutch-American astronomer named Martin Schmidt, working at the Palomar Observatory in California, and what he figured out in 1963 would turn out to be one of the most astonishing revelations in the history of astronomy. Because what Schmidt realized, staring at the spectrum of a quasar called 3C273, was that the light from this object was redshifted by an enormous amount, far more than any star in our galaxy, which meant it wasn't in our galaxy at all. It was incredibly, absurdly far away. And if it was that far away, and still that bright in our telescopes, then the amount of energy it was producing was staggering, truly, almost incomprehensibly large. We're talking about something that was outshining its entire host galaxy, an object so luminous that it was producing more energy than 100 normal galaxies combined, maybe more. And all of that energy was coming from a region of space that was, cosmically speaking, tiny, not galaxy-sized, not even solar system-sized in some cases. Just this compact, furious little engine pouring out light across the entire electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, even gamma rays, everything, all at once, at a level of power output that made every known astrophysical process look feeble by comparison. And here's the thing that really got people's attention in the 1960s. Nobody could figure out what was producing that much energy. Seriously. It was a genuine crisis. You couldn't explain it with nuclear fusion, because even the most efficient fusion reactions, the kind that power stars, couldn't come close. If you tried to pack enough stars into a small enough volume to match a quasar's luminosity, the whole thing would be gravitationally unstable. It would just collapse. You couldn't explain it with chemical reactions, obviously. You couldn't explain it with any known process. And so for a few years, quasars were genuinely mysterious. Some astronomers even proposed that maybe the redshifts were wrong, that maybe these objects weren't really that far away, that maybe some unknown physical process was mimicking the appearance of extreme distance. That's how desperate people were. When you can't explain the energy, you start questioning the distance, because if you bring the object closer, you don't need as much energy to explain its brightness. But that idea didn't hold up. The redshifts were real. The distances were real, and the energy was real. The explanation that eventually emerged, and it took a while to gain full acceptance, was gravitational energy. Specifically, the energy released by matter falling into an incredibly deep gravitational well, the kind of well that only a supermassive black hole can create. And this is worth pausing on, because it's one of those ideas that sounds simple, but is actually profoundly clever. Think about it this way. When you drop a ball from a height, it accelerates. It gains kinetic energy. The higher you drop it from, the faster it's going when it hits the ground. Now imagine dropping matter, gas, dust, shredded stars, not from a few meters up, but into a gravitational field so intense that the infalling material reaches significant fractions of the speed of light before it crosses the point of no return. At those speeds, the kinetic energy is enormous, and if that material doesn't just fall straight in, but instead spirals inward, forming a disk, what we call an accretion disk, then friction within that disk converts kinetic energy into heat, and heat into radiation. Light. Lots and lots of light. Here's what's really clever about this mechanism. It turns out that gravitational accretion onto a black hole is the most efficient energy production process known to physics, apart from matter-antimatter annihilation. Nuclear fusion, the process that powers stars, converts roughly 0.7% of the rest mass energy of hydrogen into radiated energy. That's it. Less than 1%. But accretion onto a black hole? Depending on the spin of the black hole and the geometry of the accretion disk, you can convert somewhere between 6 and 40% of the rest mass energy of the infalling material into radiation. 40%. Compare that to fusion's 0.7%. It's not even close. A black hole eating matter is pound for pound, roughly 50 times more efficient at producing energy than the nuclear furnace at the heart of a star. And that's why a relatively modest amount of matter spiraling into a supermassive black hole can outshine an entire galaxy. You don't need to consume an absurd amount of material. You just need a deep enough gravitational well and a steady supply of gas. So by the 1970s and into the 1980s, the picture was coming together. Quasars were supermassive black holes. Black holes with masses of millions to billions of times the mass of our sun, sitting at the centers of distant galaxies, actively feeding on surrounding gas, and producing these extraordinary luminosities through accretion. The reason they looked like stars in photographs was simply that the central engine was so bright it overwhelmed the light of the host galaxy. You couldn't see the galaxy. You could only see the blazing core. Now, this was already a remarkable discovery. But the truly unsettling part, the part that connects back to our central puzzle, came as astronomers started finding quasars at higher and higher redshifts. See, redshift isn't just a measure of distance. It's a measure of time. Because light travels at a finite speed, when you look at something very far away, you're seeing it as it was when the light left it. A quasar at a redshift of, say, 2 is being seen as it was roughly 10 billion years ago. A quasar at redshift 6 is being seen as it was about 12.8 billion years ago, when the universe was less than 1 billion years old. And the further back you look, the younger the universe was, and the less time there was for anything, including a supermassive black hole, to have formed. Through the 1990s and 2000s, survey after survey pushed the frontier. The Sloan Digital Sky Survey, which started collecting data in 2000, was a game changer. It systematically mapped huge swaths of the sky, and among its many contributions, it started turning up quasars at redshifts above 6. These were objects shining with the luminosity of trillions of suns, powered by black holes of 1 billion solar masses or more, and they existed when the universe was barely 900 million years old. One of the landmark discoveries came in 2001 when a team led by Xiaohui Fan at the University of Arizona announced the detection of a quasar at redshift 6.28. That pushed the record at the time and really drove home the severity of the problem, because a 1 billion solar mass black hole at that epoch is extremely difficult to explain. Let me walk you through why, because this is really the heart of the whole mystery, and it's worth understanding the math, at least at a gut level. Black holes grow by accreting matter. But there's a natural speed limit on how fast they can do this, and it's called the Eddington limit. The idea was first worked out by Arthur Eddington, the same Eddington who confirmed general relativity during the 1919 solar eclipse, a man who shows up at every important moment in early 20th century astrophysics. The Eddington limit is beautifully simple in concept. As matter falls toward a black hole and heats up, it radiates. That radiation exerts pressure, outward pressure, on the incoming material. The more matter you try to feed the black hole, the more radiation you produce, and the more that radiation pushes back against the infalling gas. At some point, the outward radiation pressure exactly balances the inward gravitational pull, and you've hit the ceiling. You can't feed the black hole any faster without blowing away your own fuel supply. This sets a maximum accretion rate, and therefore a maximum growth rate, for a black hole of any given mass. And when you do the calculation, you find that a black hole accreting at the Eddington limit will roughly double its mass every few tens of millions of years. The exact number depends on assumptions about efficiency, but a commonly used figure is about 45 million years per doubling. That sounds fast, right? Doubling every 45 million years. But now, think about where you're starting from. If your seed black hole is the remnant of a massive population 3 star, say 100 solar masses, and you need to get it up to 1 billion solar masses, that's a factor of 10 million. How many doublings is that? About 23. 23 doublings at 45 million years each is just over 1 billion years. And that's assuming continuous, uninterrupted feeding at the absolute maximum theoretical rate, with no downtime, no disruptions, no periods where the gas supply runs thin, no mergers that kick the black hole out of its gas-rich environment. In reality, maintaining Eddington rate accretion continuously for 1 billion years is almost certainly impossible. Gas supplies are patchy. Feedback from the quasar's own radiation tends to blow away the surrounding fuel. Mergers with other galaxies can temporarily disrupt the accretion flow. So in practice, you'd expect the growth to be slower, maybe much slower than the theoretical maximum. And yet there they are, billion solar mass black holes shining as quasars when the universe was 800, 900 million years old. Some of them even earlier. In 2011, a quasar called ULASJ 1120 plus 0641 was found at redshift 7.09, corresponding to just 770 million years after the Big Bang, with a black hole mass estimated at about 2 billion solar masses. And then, in 2017, the record was broken again, with the discovery of ULASJ 1342 plus 0928 at redshift 7.54, seen as it was just 690 million years after the Big Bang, harboring a black hole of roughly 800 million solar masses. Each new discovery tightened the screws on the problem. Less time available, but still these enormous black holes, sitting there, fully formed, as if they'd had all the time in the world. And then came the James Webb Space Telescope. JWST, launched on Christmas Day 2021, was designed in part to see the earliest objects in the universe, and it has not disappointed. In fact, it's made the problem worse, gloriously, fascinatingly worse, because JWST has found evidence of active supermassive black holes at even higher redshifts, pushing into the first few 100 million years after the Big Bang. Some of these are not the billion solar mass monsters found by ground-based surveys. They're smaller, maybe 1 million to 10 million solar masses. But they're still far too massive to have grown from stellar remnants in the time available. And there are a lot of them, more than anyone expected. The early universe, it turns out, was teeming with actively growing black holes, embedded in small, young galaxies that were themselves still assembling. This is where the detective story gets really interesting, because now theorists have to get creative. If you can't grow 1 billion solar mass black hole from 100 solar mass seed in the time available, then you have basically 3 options. Either the seeds were much bigger than we thought, or the growth was much faster than the Eddington limit allows, or both. And each of those options has its own fascinating physics, its own set of predictions, and its own problems. The question of seed mass, how big were the first black holes really, has become one of the most active areas of research in astrophysics. And it turns out there are several competing ideas each with a different flavor of cleverness. The stellar remnant pathway, the one we already talked about, gives you seeds of maybe 100 solar masses, possibly up to a few hundred if the population 3 stars were truly enormous. But there's another idea, one that's been gaining traction over the past couple of decades, and it involves something called direct collapse. The concept is elegant and a little bit wild. Instead of forming a massive star that then dies and leaves behind a black hole, what if, under the right conditions, an entire massive gas cloud could collapse directly into a black hole without ever becoming a star at all? No nuclear fusion, no stellar lifetime, no supernova, just a cloud of primordial gas, tens of thousands or even 100,000 solar masses worth, falling inward under its own gravity and forming a black hole almost immediately. The seed you'd get from that process wouldn't be 100 solar masses. It could be 10,000 or 100,000. And that changes the arithmetic dramatically, because if your seed is already 100,000 solar masses, you don't need nearly as many doublings to reach 1 billion. Instead of needing roughly 23 doublings from 100 solar mass seed, you'd need maybe 13 or 14 doublings from 100,000 solar mass seed. And 13 doublings at 45 million years, each comes out to around 600 million years. That's still tight, but it's within the window. It's plausible. You can actually make the numbers work without invoking anything exotic about the growth rate itself. The seed just has to be big enough at the start. So how would this actually happen? How does a gas cloud skip the whole star formation step and collapse straight into a black hole? This is where the physics gets really delicate and, honestly, really beautiful. Let's think about what normally happens when a gas cloud starts to collapse. Gravity pulls the gas inward, and as it compresses, it heats up. Hot gas radiates energy. It glows, essentially. And as it loses that energy through radiation, it cools down, which allows it to compress further, which makes it fragment into smaller, denser clumps, and those clumps eventually become individual stars. This fragmentation is the key thing. It's why a single giant molecular cloud in our own galaxy doesn't just form one enormous star. It breaks apart into hundreds or thousands of smaller stars instead. Cooling enables fragmentation, and fragmentation is what makes stars. But here's the thing. What if you could prevent the gas from cooling efficiently? What if you could keep it hot enough that it couldn't fragment? Then the entire cloud, or at least a huge portion of it, would collapse as a single coherent mass. No fragmentation. No star formation, just one enormous infall of gas. And the object that forms at the center of that collapse would be so massive, tens of thousands of solar masses, that it would essentially be born as a black hole, or at least as something called a quasi-star, a bizarre, short-lived object that's basically a black hole already forming inside a giant envelope of infalling gas. So the question becomes, what keeps the gas from cooling? And this is where the story gets really specific and really clever. The main coolant for primordial gas, gas that has no metals, no dust, no carbon or oxygen or any of the heavier elements that are so good at radiating away energy, the main coolant is molecular hydrogen, H2. 2 hydrogen atoms bonded together. Molecular hydrogen can radiate energy at relatively low temperatures, and it's what allows primordial gas clouds to cool down enough to form those first population 3 stars we talked about earlier. Without molecular hydrogen, primordial gas can really only cool through atomic hydrogen transitions, and those require much higher temperatures, around 10,000 Kelvin. So if you're a gas cloud made of pristine primordial hydrogen and helium, and you have molecular hydrogen available, you can cool down to a few hundred Kelvin, fragment, and form stars. But if something destroys your molecular hydrogen, if something breaks apart those H2 molecules before they can do their cooling work, then you're stuck at much higher temperatures. The gas stays hot and smooth and doesn't fragment, and the whole cloud can collapse as one big lump. And what destroys molecular hydrogen? Ultraviolet radiation. Specifically, radiation in a particular energy range called the Lyman-Werner band, photons with energies between about 11.2 and 13.6 electron volts. These photons are really good at dissociating molecular hydrogen. They get absorbed by the H2 molecule and kick it into an excited state from which it falls apart into two individual hydrogen atoms. And here's the key insight. If a primordial gas cloud happens to be sitting near another galaxy, or near a cluster of hot young stars that are pouring out Lyman-Werner radiation, that radiation can flood through the cloud and systematically destroy all the molecular hydrogen before it can cool the gas. The cloud is bathed in this dissociating ultraviolet light. It can't cool, it can't fragment, and if it's massive enough, it just collapses wholesale. This is the direct collapse black hole scenario, often abbreviated DCBH in the literature. The idea was developed and refined by a number of theorists over the years. Mitch Begelman, Zoltan Hyman, Volker Braun, and others made crucial contributions starting in the early 2000s. And it's a genuinely elegant solution to the seed mass problem. You start with a primordial halo of gas, a dark matter halo that's accumulated maybe 10 million solar masses of baryonic matter, and you need it to be in a very specific environment. It has to be close enough to a source of Lyman-Werner radiation to suppress molecular hydrogen formation, but not so close that it's already been ionized or disrupted by that same radiation source. It's a Goldilocks situation. The radiation field has to be just right. Now, you might be thinking, how common would that situation actually be? And that's exactly the right question, because it gets at the biggest weakness of the direct collapse model. The conditions required are quite specific. You need a pristine gas cloud with essentially zero metal enrichment, because even tiny traces of metals or dust provide alternative cooling pathways that would allow fragmentation. You need a strong Lyman-Werner radiation field from a nearby source. You need the cloud to be massive enough and to have the right angular momentum properties so that it doesn't just form a disk that fragments anyway. When you put all those requirements together, the number of halos in the early universe that would actually satisfy all of them simultaneously turns out to be pretty small. Different simulations give different answers, but the estimates range from maybe one suitable halo per cubic gigaparsec, which is a huge volume of space, to maybe a few hundred per cubic gigaparsec if you're more optimistic about the conditions. And that matters, because we're not just trying to explain one or two early quasars. JWST is finding these things all over the place. If direct collapse only works in extremely rare environments, it might explain the most extreme, most luminous quasars at high redshift, the real monsters, the billion solar mass behemoths at redshift 7 or 8. But it might not explain the much more common population of million to 10 million solar mass black holes that JWST is uncovering in ordinary-looking early galaxies. So direct collapse might be part of the answer, but probably not the whole answer. There's another seed formation pathway that's been getting a lot of attention, and it sits somewhere in between the stellar remnant idea and the direct collapse idea. It involves dense star clusters. Picture one of those early dark matter halos, a few 100 million years after the Big Bang, where gas has cooled and fragmented and formed a dense cluster of stars, maybe thousands of stars packed into a very small volume. In a cluster, that dense, stars interact with each other gravitationally. They scatter off each other, they form binary systems, and occasionally two stars physically collide and merge. In a really dense, compact cluster, this process of runaway stellar mergers can happen very quickly, faster than the individual stars can evolve and explode as supernovae. So you get a situation where collisions keep building up a single object at the center of the cluster, merger after merger, until you've assembled something with 1,000 or several thousand solar masses. That object eventually collapses into a black hole, and you've got an intermediate mass seed, bigger than what you'd get from a single population 3 star, though not as big as a direct collapse black hole. This idea has a nice feature. It doesn't require the extremely specific environmental conditions that direct collapse demands. Dense star clusters can form in a wider range of circumstances. The challenge is in the details of the dynamics. You need the mergers to happen fast enough before stellar evolution removes stars from the cluster through supernovae, and you need the cluster to be dense enough that the collision rate is high. Groups like those led by Bhaskar Agarwal, Mohammed Latif, and others have run sophisticated simulations of this process, and the results are encouraging but still uncertain. The seeds you get are typically in the range of 1,000 to maybe 10,000 solar masses, intermediate between the other two pathways. So now you've got 3 seed formation channels, stellar remnants giving you seeds around 100 solar masses, runaway cluster mergers giving you seeds of roughly 1,000 to 10,000 solar masses, and direct collapse giving you seeds of 10,000 to 100,000 solar masses. Each has different requirements, different probabilities, and different predictions for what we should observe. And here's what's really fun about this. They're not mutually exclusive. All 3 could have been operating simultaneously in the early universe, in different environments, producing a spectrum of seed masses. Some halos might have formed population 3 stellar remnants. Others, in denser environments, might have produced cluster merger seeds, and a rare few, in just the right Goldilocks conditions, might have undergone direct collapse. The early universe might have been seeding black holes through multiple channels at once, but even with bigger seeds, you still have a growth problem. Even 100,000 solar mass direct collapse black hole needs to grow by a factor of 10,000 to become a billion solar mass quasar. And if growth is limited by the Eddington limit, that still takes hundreds of millions of years of continuous, uninterrupted accretion at the maximum possible rate. Continuous is the key word there. In reality, accretion is messy. Gas supplies are intermittent. Mergers disrupt things. The black hole's own radiation can blow away its food supply. So even with generous seeds, many astrophysicists suspect you also need episodes of super Eddington accretion, periods where the black hole is somehow eating faster than the Eddington limit would seem to allow. Now, when we talked about the Eddington limit earlier, I described it as a balance between gravity pulling gas in and radiation pressure pushing gas out. And that's true, but it's true for a specific geometry, spherical accretion, where gas is falling in uniformly from all directions and radiation is pushing outward uniformly in all directions. But real accretion isn't spherical. Real accretion involves disks. Gas spirals in through a flattened disk, and the radiation comes out primarily from the inner regions of that disk and from the poles of the black hole. And this geometric mismatch is the key to super Eddington accretion. Imagine gas flowing in through the equatorial plane, through the disk, while radiation escapes preferentially along the polar axis, perpendicular to the disk. The radiation isn't hitting the incoming gas head-on, It's escaping out the sides, so to speak. This means the incoming gas along the equator can keep flowing in even while the total luminosity exceeds the Eddington limit, because the radiation is being funneled away from the accretion flow. The technical term for this is photon trapping, or advection-dominated accretion. At very high accretion rates, the gas is flowing inward so fast that photons generated in the inner disk get swept inward along with the gas before they have a chance to diffuse outward and push against the incoming material. The radiation gets trapped in the flow and carried into the black hole, which means it never exerts the outward pressure that would otherwise shut down accretion. This isn't just theoretical hand-waving. There's a well-developed framework for this called slim disk accretion, which was worked out in detail by Abramowitz and colleagues in the late 1980s, building on earlier work by Begelman. In the slim disk model, accretion rates can exceed the Eddington rate by factors of several, maybe even factors of 10 or 100 in extreme cases. The black hole is essentially gorging itself, growing much faster than the simple Eddington calculation would predict. And the radiation that does escape comes out in narrow beams along the poles, creating a distinctive observational signature that we might actually be able to detect. Here's what's really exciting about this. JWST may already be seeing evidence of super Eddington accretion in action. Some of the high redshift black holes it's detected have properties that are hard to explain with standard Eddington-limited growth. They're too massive for their host galaxies, or their spectra show signs of unusually dense, fast-moving gas that suggests very high accretion rates. A particularly intriguing case is a black hole detected in a galaxy called GN-Z11, which is one of the most distant galaxies known, seen as it was just about 400 million years after the Big Bang. The black hole in GN-Z11 appears to have a mass of around 1 to 2 million solar masses, which doesn't sound enormous compared to the billion solar mass quasars. But at that early epoch, even 1 million solar masses is really hard to explain unless either the seed was very large or the growth was super Eddington or both. And this brings us to something that I think is one of the most profound shifts in how we understand galaxy formation, a shift that JWST has accelerated dramatically. For decades, the standard picture was that galaxies form first and black holes come later, that you build up a galaxy through mergers and gas accretion, and somewhere along the way, a black hole forms at the center and grows gradually. But the early universe black holes that JWST is revealing are challenging that narrative in a really fundamental way. Some of these black holes are shockingly massive relative to their host galaxies. In the local universe, there's a well-known relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge. The black hole is typically about 0.1% of the bulge mass. But some of these early JWST black holes seem to be a much larger fraction of their host galaxy's mass, maybe 1% or even 10%. The black holes are, in a sense, too big for their galaxies, or maybe it's more accurate to say the galaxies haven't caught up yet. This raises a fascinating chicken and egg question that astronomers are actively debating right now. Did the black holes form first and then help build the galaxies around them? Or did they form simultaneously, but the black holes grew faster in the early universe than the galaxies did? There's even a provocative idea, championed by some theorists, that massive black hole seeds in the early universe could have actually stimulated galaxy formation, that the energy output from an accreting black hole could have compressed surrounding gas and triggered star formation, essentially building its own galaxy from the inside out. It's a complete inversion of the traditional picture, and while it's still speculative, the JWST data is making people take it seriously in a way they wouldn't have even 5 years ago. And that's one of the things that makes this moment in astrophysics so exciting. The data is outrunning the theory, which is exactly when the most interesting science happens. So let's sit with this idea for a minute, because it really is a profound shift in how we think about the architecture of the universe. Imagine you're looking at a galaxy like the Milky Way today. It's this enormous structure, hundreds of billions of stars, a disk of gas and dust, 100,000 light-years across, spiral arms, a central bulge, a halo of dark matter extending even further. And sitting right at the center is Sagittarius A star, our supermassive black hole, about 4 million solar masses. That sounds like a lot, but compared to the galaxy as a whole, it's tiny. The Milky Way's total mass is something like 1 trillion solar masses when you include the dark matter halo. So the black hole is this relatively modest thing sitting at the heart of a vast structure. The galaxy came first, in a sense. It built itself up over billions of years through mergers and gas accretion, and the black hole grew along with it, but always stayed proportional. Always stayed in that roughly 0.1% relationship with the bulge. Now rewind to the universe at, say, 400 million years old. What JWST is showing us in some cases is almost the opposite arrangement. You've got a black hole that might be 1 million solar masses, maybe 10 million, sitting inside a galaxy that's barely there. A small, faint collection of stars that hasn't had time to grow much yet. The black hole isn't 0.1% of the galaxy's mass. It might be 1%, 5%, in extreme cases, maybe even more. The proportions are all wrong compared to what we see locally. It's as if you found a fully grown oak tree's root system underneath a sapling. The underground part is way too developed for what's growing above the surface. And here's what's really interesting about this. It's not just a curiosity. It actually tells us something about how the black hole and the galaxy interact, how they regulate each other's growth over cosmic time. In the local universe, there's this beautifully tight correlation between black hole mass and bulge mass, and also between black hole mass and the velocity dispersion of stars in the bulge. That's the M-sigma relation, first clearly established around the year 2000 by Carl Gebhardt and his collaborators, and independently by Laura Ferraris and David Merritt. This correlation is remarkably tight. Black holes that have no business knowing about stars orbiting thousands of light-years away somehow end up with masses that are precisely correlated with those stars' motions. It implies that the black hole and the galaxy are in a conversation, a feedback loop that regulates both of their growth over billions of years. The mechanism for that conversation is something called AGN feedback, active galactic nucleus feedback. When a black hole is actively accreting, it doesn't just quietly swallow gas. It releases enormous amounts of energy, radiation, jets of relativistic particles, powerful winds that can blow at thousands of kilometers per second. That energy output can heat the surrounding gas, push it away, even expel it from the galaxy entirely. And when you remove gas from a galaxy, you shut down star formation, because stars form from cold, dense gas. No gas, no new stars. So the black hole, by growing and feeding, actually limits the galaxy's ability to grow. But here's the flip side. When the black hole blows away the gas, it also cuts off its own food supply. So it stops accreting, quiets down, and eventually gas cools and flows back in, restarting the cycle. It's a thermostat. The black hole and the galaxy are regulating each other, and over billions of years, This back and forth drives them toward that tight correlation we observe today. But in the early universe, that thermostat hasn't had time to reach equilibrium yet. The black hole might be in a phase of rapid growth, maybe super Eddington accretion, maybe fed by dense streams of pristine gas flowing along dark matter filaments, and it's outpacing the galaxy's ability to form stars. Or alternatively, the feedback from the black hole might actually be enhancing star formation in some cases, not suppressing it. This is the provocative idea I was starting to describe, that in the right conditions, the energy from an accreting black hole can actually compress nearby gas clouds and trigger them to collapse into stars, rather than blowing them apart. Think about it this way. If you have a powerful wind blowing outward from a central black hole, and that wind runs into a dense clump of gas, what happens depends on the details. If the gas is diffuse, the wind might just scatter it, heat it up, blow it away. That's negative feedback. It suppresses star formation. But if the gas is already fairly dense, the wind can actually squeeze it further, compress it past the threshold where gravity takes over, and it collapses into stars. That's positive feedback. The black hole is literally helping to build the galaxy around it. And in the early universe, where gas densities were generally higher and everything was more compact, positive feedback might have been more common than it is today. This idea has been explored theoretically by people like Joe Silk at Johns Hopkins and the Institut d'Astrophysique de Paris, and by Andrea Ferrara and others. Silk, in particular, has written extensively about what he calls the black hole first scenario, where massive seed black holes form early and their feedback helps sculpt the first galaxies. It's not universally accepted, far from it, but it's a serious theoretical framework that makes specific predictions about what early galaxies should look like. And some of those predictions are lining up surprisingly well with what JWST is finding. Now, here's where I want to slow down and talk about something that JWST has revealed that nobody really expected, and it connects to all of this in a beautiful way. Starting in 2023 and continuing into 2024, several teams using JWST identified a population of compact, red objects at very high redshifts. We're talking redshifts of 5, 6, 7, sometimes higher. These objects are tiny, almost point-like, and they're red not because they're old and cool, but because they're heavily obscured by dust, or because their light is dominated by emission from hot gas around an accreting black hole. They've been nicknamed little red dots, which is charmingly informal for something that might represent a fundamentally new phase of galaxy and black hole evolution. The little red dots are fascinating because they seem to be caught in the act of that early co-evolution I was just describing. Many of them show spectroscopic signatures of both active black hole accretion, broad emission lines indicating gas moving at thousands of kilometers per second near a central black hole, and active star formation happening simultaneously. They're compact, they're luminous, and they're surprisingly common. Some estimates suggest there are far more actively accreting black holes in the early universe than anyone had predicted based on pre-JWST models. And here's the thing that's really puzzling people. If you take the broad emission lines at face value and use standard techniques to estimate the black hole masses, you get numbers that are uncomfortably large. Black holes of 10 million, 100 million, sometimes even 1 billion solar masses at redshifts where the universe is less than 1 billion years old. Now, some astronomers argue that the standard mass estimation techniques might not apply cleanly to these objects, that the geometry of the gas might be different, or that the broad lines might be partly produced by powerful outflows rather than gravitationally bound gas orbiting the black hole. That would mean the masses are being overestimated. This is an active and sometimes heated debate in the community right now. Papers are going back and forth, with different groups analyzing the same JWST spectra and reaching different conclusions about what the black hole masses actually are. But even the conservative estimates suggest that these early black holes are more massive and more numerous than pre-JWST models predicted. And that brings us back to the seeding problem we talked about earlier, but now with sharper teeth. It's not just that you need to explain how 1 or 2 exceptional quasars got so massive so fast. That was the challenge from ground-based surveys. Now you need to explain a whole population of overly massive black holes scattered across the early universe. That's a much harder problem, and it's pushing theorists to consider whether multiple seeding channels were all operating simultaneously. Direct collapse seeds here, runaway mergers there, maybe even some exotic pathways that haven't been fully explored yet. One of those more exotic ideas involves primordial black holes that didn't form from stars at all, but from density fluctuations in the very early universe, within the first second after the Big Bang. This is a concept that goes back to Stephen Hawking and Bernard Carr in the 1970s. The idea is that if certain regions of the infant universe were slightly denser than their surroundings, and we know from the cosmic microwave background that density fluctuations existed, some of those regions might have been dense enough to collapse directly into black holes before any stars, any galaxies, any large-scale structure existed at all. These primordial black holes could in principle have any mass, depending on when during the early universe they formed. Ones forming earlier would be smaller. Ones forming at just the right moment could be thousands or millions of solar masses. For decades, primordial black holes were a theoretical curiosity. Interesting, but largely untestable. There are observational constraints that rule them out as the dominant form of dark matter across most mass ranges, which was one of the more exciting possibilities people had considered. But as seeds for supermassive black holes? That's a different question, and it's gotten new life recently. If even a small number of primordial black holes with masses of, say, 10,000 to 100,000 solar masses survived from the first fraction of a second after the Big Bang, they'd be sitting there in the dark ages, ready-made seeds, already massive enough to start accreting and growing, without needing any of the complicated astrophysics of direct collapse or stellar mergers. They'd have a huge head start. The challenge is that the formation of primordial black holes requires very specific conditions in the early universe. The density fluctuations on the relevant scales need to be much larger than what the standard inflationary model predicts. So you'd need some modification to inflation, some feature in the primordial power spectrum that enhances fluctuations on small scales while keeping the large-scale fluctuations consistent with what we observe in the cosmic microwave background. It's possible, and there are inflationary models that produce exactly this kind of feature, but it's adding a layer of theoretical machinery that makes some people uncomfortable. You're invoking something that happened in the first tiny fraction of a second after the Big Bang to explain something you're observing billions of years later. It's a long causal chain. Still, it's on the table. And what I find beautiful about this whole landscape of ideas is how it connects the very largest scales of the universe, cosmology, the Big Bang, inflation, to the very smallest scales of black hole physics and the detailed astrophysics of gas dynamics and star formation. The question of where the first supermassive black holes came from is not just an astrophysics question. It's a question that reaches all the way back to the initial conditions of the universe itself. And speaking of initial conditions, there's another thread we should pull on because it connects to something that JWST has revealed that's arguably even more unsettling than the overly massive black holes. It has to do with the galaxies themselves, not just the black holes at their centers, but the stellar populations, the overall masses of the galaxies at very early times. Because starting in the first year of JWST operations, multiple teams began reporting galaxies at very high redshifts that appeared to be far more massive and far more mature than anyone had expected. Galaxies at redshifts of 9, 10, even beyond 12 that seemed to contain hundreds of millions or even billions of solar masses worth of stars, already assembled into relatively organized structures. And this was a genuine shock, not a mild surprise, not a, that's interesting kind of result. This was the kind of finding that made people sit up in their chairs and start questioning assumptions they'd held for decades. Because the models, the careful, well-tested models of how galaxies assemble over cosmic time, those models had clear predictions about what you should see at redshifts of 9, 10, 12, and what JWST was showing didn't match. Let me set the stage for why this was so jarring. Before JWST, the standard picture of galaxy formation was hierarchical. That word, hierarchical, is important. It means things build up from small pieces. You start with tiny clumps of dark matter and gas, little halos that form shortly after the Dark Age's end, and these small halos merge together over time, pulling in more gas, forming more stars, merging with other small halos to make medium halos, and those medium halos merge to make larger ones. It's a bottom-up process. Think of it like building a city. You don't start with skyscrapers. You start with a few huts, then villages, then towns, and eventually you get a metropolis. The universe, according to this picture, works the same way. The biggest, most massive galaxies, the ones like our Milky Way or even larger elliptical galaxies, those are late arrivals. They're the product of billions of years of merging and accumulation. At very early times, say within the first 500 or 600 million years after the Big Bang, you should see only the huts, small, scrappy, irregular little galaxies with maybe a few million solar masses of stars, maybe tens of millions if you're lucky, not billions. And this picture wasn't just a guess. It was built on a framework called Lambda CDM, Lambda Cold Dark Matter, which is basically the standard model of cosmology. Lambda refers to the cosmological constant, which drives the accelerating expansion of the universe, and CDM refers to cold dark matter, the invisible scaffolding that gravitationally shapes where galaxies form. Lambda CDM has been spectacularly successful. It matches the cosmic microwave background observations from WMAP and Planck with extraordinary precision. It predicts the large-scale distribution of galaxies, the cosmic web of filaments and voids, beautifully. It gets the abundance of galaxy clusters right. It's one of the great achievements of modern physics. So when your observations start pushing against the predictions of Lambda CDM, people pay attention, and they get nervous. Now, what JWST found. In the summer of 2022, within just the first few weeks of science operations, teams started identifying candidate galaxies at extraordinarily high redshifts. Redshift 7, 8, 9, those were expected. But then candidates started appearing at redshift 10, 11, 12, and some groups were claiming objects at redshift 13, 14, even beyond 16. The initial reaction was cautious excitement mixed with healthy skepticism, because photometric redshifts estimated from the colors of an object rather than from a direct spectrum, can be fooled. A dusty galaxy at redshift 5 can sometimes mimic the colors of a clean galaxy at redshift 12. So there was a period of intense back and forth, checking and rechecking. But as spectroscopic confirmations started coming in from instruments like NIRSpec on JWST, the picture solidified. There really were galaxies out there at redshifts of 10, 11, 12, and they really were more luminous, more massive, and more structurally mature than the models predicted. One of the early headline results came from a galaxy called Glass Z13, later refined and joined by others like JD's GSZ130, which was spectroscopically confirmed at a redshift of about 13.2. That puts it roughly 320 million years after the Big Bang. 320 million years. And it wasn't just a faint smudge. It had a detectable stellar mass, an organized morphology, evidence of ongoing star formation. Another galaxy, called Maisie's Galaxy, was confirmed at around redshift 11.4 by the Sears survey team, led by Stephen Finkelstein at the University of Texas. These were real objects, genuinely sitting in the epoch when the universe was barely getting started. But here's the thing that really caused the stir. It wasn't just that these galaxies existed. It was how massive some of them appeared to be. When you fit the observed light from these galaxies with stellar population models, trying to figure out how many stars they contain, what ages those stars are, how much dust is present. Some of the results were coming back with stellar masses of hundreds of millions of solar masses. A few candidates were pushing toward 1 billion. And that creates a timing problem that's conceptually very similar to the black hole timing problem we talked about earlier, but in some ways even more severe. Think about it this way. To have 1 billion solar masses of stars in place by 400 million years after the Big Bang, you need to have formed those stars. Stars form from gas. The gas has to cool, collapse into dense clouds, fragment, and ignite nuclear fusion. That takes time. And the star formation rate can't be arbitrarily high. There are physical limits on how fast gas can cool and how efficiently it converts into stars. In the local universe, galaxies typically convert only a few % of their available gas into stars during any given dynamical time, the time it takes for the system to undergo one gravitational freefall cycle. This is called the star formation efficiency, and it's usually quite low, maybe 2 to 5%. The reason it's low is because of all the feedback processes we talked about: supernova explosions blowing gas out, radiation pressure from hot stars, turbulence stirring things up. All of these conspire to keep star formation relatively sluggish. So if you want 1 billion solar masses of stars in 400 million years, and your star formation efficiency is, say, 3% per dynamical time, you need an enormous reservoir of gas, and you need multiple cycles of collapse and star formation, and you need everything to start very early. When people ran the numbers within the standard lambda CDM framework, the predicted abundance of such massive galaxies at these redshifts was extremely low. Some early analyses suggested the observed galaxies exceeded the predicted number density by factors of 10 or even 100. That's not a small discrepancy. That's the kind of mismatch that either means your observations are wrong, your interpretation of the observations is wrong, or your model is missing something fundamental. And this is where the community split into camps, much like it did with the black hole seeding problem. One camp said, "Let's not panic. Photometric masses are uncertain. The stellar population models we're using to convert light into mass have assumptions baked in. Assumptions about the initial mass function, about dust, about star formation histories, and if any of those assumptions are off, the masses could be overestimated. Maybe these galaxies are less massive than they look. Maybe they're dominated by very bright, young, massive stars that produce a lot of light per unit mass, making the galaxy appear heavier than it really is." This is a real concern, and subsequent work has indeed revised some of the most extreme mass estimates downward. But the other camp pointed out that even after you apply conservative corrections, even after you account for the known uncertainties, you're still left with more massive galaxies at high redshift than the standard models comfortably predict. The tension is reduced but not eliminated. And the sheer number of these objects, it's not one weird outlier, it's a population, makes it harder to dismiss. So what could explain it? Well, one possibility is that star formation in the early universe was simply more efficient than it is today. Maybe the feedback processes that regulate star formation in nearby galaxies hadn't fully kicked in yet. If the first generation of galaxies could convert, say, 20 or 30% of their gas into stars per dynamical time instead of 3%, that would go a long way toward explaining the observations. And there are theoretical reasons to think this might be the case. The gas in early galaxies was more pristine, lower in heavy elements, which changes how it cools and fragments. The cosmic environment was denser, with more frequent mergers delivering fresh gas. And crucially, the feedback from supermassive black holes, the AGN thermostat we discussed, might not have been fully operational yet, precisely because those black holes were still growing. Without that thermostat throttling things back, star formation could have run hotter and faster. And notice how this connects back to the black hole story. If the black holes were still small, still growing, still below the mass where their feedback becomes dominant, then the galaxies could form stars more freely. But that means the galaxies get massive quickly, while the black holes lag behind, which is exactly the opposite of what some of the little red dot observations suggest, where the black holes seem overly massive relative to their host galaxies. So you've got this fascinating tension. Some early systems seem to have black holes that are too big for their galaxies, and other early systems seem to have galaxies that are too big for their black holes, or maybe too big for the universe's timeline, period. It's as if the early universe was a more extreme place in every direction. More massive black holes, more massive galaxies, more of everything, faster than expected. Another possibility, and this one is more radical, is that the issue isn't with astrophysics at all, but with cosmology. Maybe lambda CDM itself needs modification. Maybe the initial conditions, the spectrum of density fluctuations coming out of inflation, had more power on small scales than we assumed. That would mean more small, dark matter halos forming earlier, which means more sites for early galaxy formation, which means more massive galaxies at high redshift. This connects directly to the primordial black hole story, actually, because enhanced small-scale fluctuations are exactly what you need to make primordial black holes too. So there's a version of this where a single modification to the inflationary power spectrum simultaneously eases the tension with early massive galaxies and provides seeds for early supermassive black holes. It's elegant in a way. One tweak, two problems solved. But it's speculative, and the constraints from the cosmic microwave background are tight, so the modification has to be carefully tuned to affect only the right range of scales. There's also been discussion about whether our understanding of dark matter itself might need revision. What if dark matter isn't perfectly cold? What if it has some small self-interaction or some warm component that changes how structures form on small scales? These are ideas that have been floating around for years to address other small-scale problems with lambda CDM. Things like the too big to fail problem and the cusp core problem in dwarf galaxies. And the JWST observations have given them new relevance. But let me bring this back to something concrete, because I think the most interesting aspect of all this isn't any single explanation. It's the way these different puzzles are starting to interlock. The early massive black holes, the early massive galaxies, the little red dots, the question of feedback, the question of seeding, the question of star formation efficiency. These aren't separate problems. They're all facets of the same deep question. What happened in the first billion years? How did the universe go from a smooth, featureless fog of hydrogen and helium to the richly structured cosmos we see today? And did it do so faster and more dramatically than we thought? And this is where a particular set of JWST observations becomes really important, because they don't just show us that early galaxies are massive. They show us something about the structure of those galaxies that adds yet another layer of surprise. Some of these high redshift galaxies appear to have disk-like morphologies, organized, flattened, rotating structures that look remarkably like the spiral galaxies we see in the nearby universe. And that was genuinely not expected, because in the hierarchical picture, early galaxies should be messy. They should be irregular, disturbed, showing signs of recent mergers. The fact that some of them appear to have settled into ordered disks so quickly suggests that either the merging process was less violent than we assumed, or that disk formation can happen much faster than our simulations predicted, or both. A team led by Leonardo Ferreira published results in 2022 showing that a significant fraction of galaxies at redshifts above 3 had disk-like structures, and subsequent JWST imaging has pushed this finding to even higher redshifts. Now, I want to be careful here, because morphological classification at these distances is tricky. You're working with a handful of pixels, and what looks like a disk could be something else viewed at a particular angle. But the statistical trend is real, and it's forcing simulators to go back and look at their models with fresh eyes. And some of the newest simulations, particularly those run with very high resolution and updated physics, are actually starting to produce early disks more readily than older simulations did. So it may be that the models weren't fundamentally wrong, just not quite detailed enough. But all of this, the masses, the morphologies, the black holes, it all feeds into a growing sense that the first billion years of cosmic history were more dynamic, more productive, and more interesting than the pre-JWST consensus suggested. And that brings us to something I find really compelling, which is the role of environment. Because not all parts of the early universe were created equal. Some regions were denser than others from the very beginning, thanks to those primordial density fluctuations we keep coming back to. And in those overdense regions, everything happens faster. Halos form earlier, gas accumulates sooner, the first stars ignite more quickly, and the conditions for forming massive black hole seeds are more favorable. These overdense regions are the ancestors of what we see today as galaxy clusters, the most massive, gravitationally bound structures in the universe. And there's growing evidence that the most extreme early objects JWST is finding, the most massive galaxies, the most luminous quasars, are preferentially located in these protoclusters, these dense knots in the cosmic web where everything was happening at once. Think of it like this. If you could somehow look at the universe a few 100 million years after the Big Bang and paint it according to density, light colors for underdense voids, dark colors for the densest regions, you'd see a vast, mostly pale canvas with these scattered dark patches, these knots where matter had already begun to pile up. And in those dark patches, the cosmic clock was effectively running faster. Not literally, of course. Time passes the same everywhere. But the processes that build structure, the gravitational collapse, the cooling of gas, the ignition of stars, all of that was accelerated in regions where there was simply more raw material to work with. And here's the thing about protoclusters. They're not small. A protocluster at redshift 6 or 7 might span 10 or 20 co-moving megaparsecs, which is a huge volume, containing dozens or even hundreds of nascent galaxies, all forming in relatively close proximity. Close enough that they can interact gravitationally, exchange gas through filaments of the cosmic web, and merge with each other on timescales that would be much longer in emptier environments. So you get this compounding effect. More matter means faster halo growth. Faster halo growth means earlier gas accumulation. Earlier gas accumulation means earlier star formation and earlier black hole seeding. And the mergers between these early halos, which happen more frequently in dense environments, provide exactly the kind of rapid mass assembly that we've been struggling to explain. There's a really nice piece of observational evidence for this. In 2022 and 2023, several teams used JWST to identify what appear to be genuine protoclusters at remarkably high redshifts. One particularly striking example was reported by a group led by Takahiro Morishita, who found an overdensity of galaxies around a luminous source at redshift around 7.9, which puts it roughly 670 million years after the Big Bang. Multiple galaxies clustered together, already interacting, already building up mass cooperatively. And this wasn't an isolated finding. The CEERS survey, the same one where Stephen Finkelstein's team found Maisie's galaxy, also turned up evidence for overdense structures at high redshift. So did JADE's, the JWST Advanced Deep Extragalactic Survey, which is one of the deepest imaging campaigns ever conducted. Now, what's really compelling about this is that it starts to connect several of the puzzles we've been talking about. Remember the problem with those overmassive black holes, the ones that seem too heavy for their host galaxies? And separately, the problem with those overmassive galaxies, the ones that seem to have formed too many stars too quickly? Both of those puzzles become somewhat less puzzling if these extreme objects are preferentially forming in protoclusters. Because in a protocluster, you have enhanced merger rates, which can funnel gas towards central black holes more efficiently. You have denser gas reservoirs, which can sustain higher star formation rates. And you have the possibility of multiple black hole seeds forming in close proximity and then merging together, which is a way to build mass that doesn't care about the Eddington limit at all. Two black holes spiraling together and combining. That's not accretion. That's just gravity doing what gravity does, and there's no radiation pressure to fight against. Let's talk about that for a second, because black hole mergers are a whole separate growth channel that we haven't really explored yet. When two galaxies merge, which happens frequently in dense environments, Their central black holes can eventually find each other, spiral inward through a process called dynamical friction, and coalesce into a single, more massive black hole. This process has been studied theoretically for decades, and it's one of the key predictions of hierarchical structure formation. If galaxies grow by merging, then their black holes should merge too, and the resulting black hole should be more massive than either parent. The challenge has always been what's called the last parsec problem. When two supermassive black holes are orbiting each other in the center of a merged galaxy, dynamical friction from surrounding stars is very efficient at bringing them closer together when they're far apart, separations of hundreds or thousands of parsecs. And gravitational wave emission is very efficient at bringing them together when they're very close, separations of 1,000th of a parsec or less. But in between, at separations of roughly 1 parsec, there's this awkward middle ground where neither mechanism is particularly effective. The black holes can stall there, orbiting each other for billions of years without actually merging. At least, that was the theoretical concern. But here's what's wild. In 2023, multiple pulsar timing array collaborations, Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, all independently announced evidence for a gravitational wave background, a low-frequency hum of gravitational waves permeating all of space, exactly the kind of signal you'd expect from a cosmic population of supermassive black hole binaries slowly spiraling together and merging throughout the history of the universe. The signal was subtle, detected as correlated timing variations in millisecond pulsars scattered across the sky. But it was real, and it was consistent across all 4 experiments. Now, the amplitude of that signal, how loud the hum is, tells you something about how many mergers are happening and how massive the black holes involved are. And intriguingly, the amplitude measured by Nanograv and the other groups was somewhat higher than many theoretical models had predicted, which could mean that supermassive black holes are, on average, more massive than we thought, or that mergers happen more frequently than we thought, or both. Either way, it's another piece of evidence pointing toward a universe where black hole growth has been more vigorous than the pre-JWST, pre-pulsar timing array consensus assumed. And think about what this means for the early universe specifically. If black hole mergers are an important growth channel, and the gravitational wave background suggests they are, then protoclusters at high redshift are exactly where you'd expect the most dramatic merger-driven growth to occur. More galaxies in close proximity means more mergers. More mergers means more opportunities for black holes to combine. And each merger event can potentially double the mass of a black hole in an instant. No accretion required, no Eddington limit to worry about. You could imagine a scenario where a black hole seed forms at, say, 1,000 solar masses from direct collapse, then merges with another seed of similar mass. Then the merged remnant's host galaxy merges with a third galaxy, bringing another black hole, and so on. A few generations of mergers in a dense protocluster environment, combined with accretion between mergers, could plausibly build a billion solar mass black hole in a few 100 million years. This is speculative, I should say. We don't have direct observational proof that this specific merger chain scenario played out for any particular high redshift quasar, but the ingredients are all there, and the theoretical models that include both mergers and accretion in dense environments do a better job of reproducing the observed population of early supermassive black holes than models that rely on accretion alone. So coming back to the big picture, and this is something worth sitting with for a moment, we're arriving at a view of the early universe that's much richer and more complex than what anyone imagined even a decade ago. The story used to be relatively simple. The universe was born. It cooled. The first stars formed. They died. They left behind small black holes, and those black holes slowly grew over billions of years into the supermassive monsters we see in galaxy centers today. A neat, linear, patient narrative. And now? Now we're seeing that the early universe was running multiple growth channels simultaneously. Direct collapse creating heavy seeds. Population 3 remnants providing lighter seeds. Runaway stellar mergers in dense clusters producing intermediate mass seeds. Super Eddington accretion pushing past the classical growth limits. Black hole mergers bypassing accretion entirely. And all of this happening preferentially in protoclusters, in the densest environments where everything was amplified. It's messy. It's complicated. And honestly, it's beautiful, because it means the universe wasn't doing just one thing. It was doing everything at once, and different mechanisms dominated in different environments and at different times. The challenge for theorists now is figuring out the relative importance of each channel, which one matters most, and where, and when. And JWST is going to keep pushing on this. The telescope is still relatively early in its mission. The deep surveys are getting deeper. The spectroscopic follow-ups are getting more complete. Every few months, another paper comes out pushing the frontier to higher redshifts or finding new populations of objects that don't quite fit the existing models. It's one of those rare moments in science where the observations are genuinely ahead of the theory, where the data is surprising the people who've spent their careers building models of how this should all work. There's one more thread I want to pull on, though, before we start to bring some of these ideas together. And it has to do with something we touched on earlier. The relationship between black holes and their host galaxies. That M-sigma relation. That tight correlation between black hole mass and the velocity dispersion of stars in the galactic bulge. Because one of the most interesting things JWST has revealed is that this relationship, which holds so beautifully in the nearby universe, appears to break down at high redshift. And not just a little. Some of the earliest black holes JWST has found are 10 to 100 times more massive relative to their host galaxies than the local M-sigma relation would predict, which raises a genuinely profound question about cause and effect, about which came first, and about whether the relationship between black holes and galaxies is something that's built into the initial conditions of the universe or something that emerges gradually over billions of years of coevolution. And the answer to that question, or at least the best current thinking about it, takes us into some of the most active debates in astrophysics right now. So let's get into it. The M-sigma relation, when it was first nailed down observationally around the year 2000 by Carl Gebhardt and his collaborators, and independently by Laura Ferraris and David Merritt, was one of those results that made people sit up straight, because it was too tight, too clean. The mass of the central black hole in a galaxy correlated with the velocity dispersion of stars in the bulge, not loosely, not approximately, but with remarkably little scatter. And the relationship held across a huge range of galaxy sizes, from relatively modest systems to giant ellipticals with black holes billions of times the mass of the Sun. The correlation was so tight that it implied something deep. It implied that the black hole and the galaxy somehow knew about each other, that they had grown together in some coordinated way, despite the fact that the black hole's gravitational influence only extends over a tiny fraction of the galaxy's total volume. the sphere of influence of even a supermassive black hole is minuscule compared to the size of its host galaxy. So how could they be so precisely linked? And the answer that emerged over the next decade or so, the one we talked about earlier, was feedback. The black hole grows by accreting gas, which makes it shine as an active galactic nucleus, and that energy output drives winds and jets that heat and expel gas from the surrounding galaxy, which eventually shuts down both star formation and the black hole's own fuel supply. It's a thermostat. The black hole regulates itself and its galaxy simultaneously, and over time, this mutual regulation drives the system toward that tight M-sigma correlation. It's elegant, it's self-consistent, and it became one of the pillars of our understanding of galaxy evolution. But here's the thing. That whole picture assumes time. It assumes billions of years of back and forth, of accretion episodes and feedback cycles, of mergers that shuffle things around and gradually nudge the system toward equilibrium. And when you look at galaxies in the nearby universe, galaxies that have had 13 billion years to evolve, the relationship is beautiful. But what happens when you look at galaxies that are only a few 100 million years old? Galaxies that haven't had time for all those feedback cycles to play out? Well, JWST is telling us, and what it's telling us is fascinating. Take the case of GN-Z11, which we've come back to a few times now. This galaxy, sitting at a redshift of about 10.6, roughly 430 million years after the Big Bang, hosts a black hole that appears to be around 1 to 10 million solar masses. Now, the galaxy itself is relatively small. Its stellar mass is estimated at something like 1 billion solar masses, maybe less. If you plot that on the local M-sigma relation, the black hole is way too heavy for its galaxy. In the nearby universe, a galaxy of that stellar mass would typically host a black hole of maybe 100,000 solar masses, possibly less. GN-Z11's black hole is at least 10 times overmassive, and possibly much more. And GN-Z11 isn't alone. The population of little red dots that JWST has been uncovering, those compact, reddened sources that appear to be accreting black holes embedded in modest host galaxies, many of them show the same pattern. The black holes are too big for their galaxies, sometimes dramatically so. A study led by Kohei Inayoshi and collaborators in 2024 looked at the black hole to stellar mass ratios in these early systems and found that at redshifts above 6 or so, the typical ratio is something like 1 to 10 or 1 to 30, meaning the black hole's mass is a few percent to maybe 10% of the total stellar mass of the galaxy. In the local universe, that ratio is more like 1 to 1,000. So these early black holes are sitting in galaxies that seem almost too small to contain them, like finding a grand piano in a studio apartment. Now, you might be thinking, okay, maybe the measurements are wrong. Maybe we're overestimating the black hole masses or underestimating the galaxy masses, and that's a fair concern. These are incredibly difficult observations. The black hole masses are typically estimated from the width of broad emission lines, which gives you the velocity of gas orbiting close to the black hole, and from the luminosity of the AGN, which gives you a rough sense of scale. Both of those estimates carry significant uncertainties, and the stellar masses are estimated from the galaxy's light after you subtract the AGN contribution, which is tricky when the AGN is so bright it can dominate the total emission. So yes, there's room for systematic error. But even accounting for generous uncertainties, the trend holds. Multiple independent teams using different methods and different samples keep finding the same thing. Early black holes are overmassive relative to their hosts. The scatter is large, the individual measurements are uncertain, but the population-level signal is robust. Something real is going on. So what does it mean? Well, this is where the debate gets genuinely interesting, because there are at least two very different ways to interpret this observation, and they lead to fundamentally different pictures of how galaxies form. The first interpretation is what you might call the head start scenario. In this picture, the black hole forms first, or at least, it grows faster than its host galaxy in the early universe. Maybe the seed was massive to begin with, a direct collapse black hole of 100,000 solar masses. Maybe it experienced a period of rapid, possibly super Eddington accretion before the galaxy had time to build up much stellar mass. In this scenario, the M-sigma relation isn't a primordial feature. It's something that develops later, as the galaxy gradually catches up. The black hole sits there, already massive, and over the next several billion years, the galaxy assembles around it through mergers and star formation, and the feedback processes we talked about slowly bring the system into alignment with the local M-sigma relation. Joe Silk has been one of the strongest advocates for this kind of picture, arguing that in some cases, the black hole might actually be the thing that triggers galaxy formation, that the energy output from the early AGN compresses surrounding gas and promotes star formation in a shell around it. The second interpretation flips this around. Maybe it's not that the black holes are too big. Maybe the galaxies are too small. Or more precisely, maybe the galaxies haven't finished assembling yet. In this picture, the black hole and the galaxy are both growing, but the stellar mass we observe at high redshift is just the beginning. The galaxy will eventually grow much larger through continued star formation and mergers, and as it does, it'll move toward the local M-sigma relation naturally. The black hole isn't anomalously massive. The galaxy is just anomalously young. This is a more conservative interpretation, and it's certainly plausible. The challenge is that some of these early systems have black holes that are so overmassive that the galaxy would need to grow by a factor of 100 or more without the black hole growing much at all, and that's hard to arrange physically. If gas is flowing in to form stars, some of it is going to find its way to the center and feed the black hole too. There's a third possibility that's more radical, and it connects back to something we discussed when we talked about primordial black holes. If the seeds themselves were very massive, if some process in the early universe, whether it's direct collapse, primordial density fluctuations, or something more exotic, produced black holes that were already millions of solar masses before galaxies even began to form, then the initial conditions would naturally produce overmassive black holes in undersized galaxies. The M-sigma relation in this picture isn't a cause, it's a consequence. It emerges over cosmic time as galaxies grow around pre-existing massive black holes and feedback gradually tunes the system. The relationship we see locally would be an attractor, a state that systems evolve toward, not a rule that's imposed from the start. And here's what makes this debate so hard to resolve. All three of these scenarios can, with the right assumptions, produce something that looks like what JWST is observing. The data we have right now can't definitively distinguish between them. What we need is more information, more precise black hole mass measurements, better stellar mass estimates, and crucially, measurements at intermediate redshifts in the range of 3 to 6, where we can watch the transition from overmassive black holes to the tight local relation. If the M-sigma relation snaps into place relatively quickly, say by redshift 4 or 5, that tells us one thing. If it takes much longer, if there are still significantly overmassive black holes at redshift 2 or 3, that tells us something very different. There's a beautiful study by Shuheng Ding and collaborators published in 2023 that used JWST imaging to measure the host galaxy properties of a sample of quasars at redshifts around 2 to 3, so not the most extreme distances, but far enough back to test the evolution of the M-sigma relation. And what they found was suggestive. The black holes in their sample were overmassive compared to the local relation, but not as dramatically as the redshift 10 systems. The offset was maybe a factor of 3 to 10, rather than a factor of 30 to 100, which hints at a gradual convergence, the relationship tightening over time as galaxies catch up. Think about what that means for a second. It suggests that the universe doesn't start with a neat, tidy relationship between black holes and galaxies. It starts messy. The early universe is a place where black holes can outpace their hosts, where the proportions are all wrong by local standards, where the feedback mechanisms that will eventually bring order haven't had time to fully operate. And then, over billions of years, through countless cycles of accretion and outflow, through mergers that mix and shuffle stellar populations, through the slow gravitational dance of dark matter, halos growing and combining, the system relaxes into the elegant correlation we observe nearby. The M-sigma relation isn't a law of physics. It's an emergent property, a pattern that arises from process, from time, from the accumulated effects of billions of years of cosmic evolution. And that's a genuinely profound shift in perspective. For years, theorists built models that treated the M-sigma relation as something fundamental, something that had to be satisfied at all times. They tuned their feedback prescriptions to reproduce it. They used it as a constraint on black hole seed masses and accretion histories. And now, JWST is suggesting that it might not apply in the early universe at all, that it's a destination, not a starting point. This has practical consequences for how we model galaxy formation. The big cosmological simulations, Illustris, TNG, Eagle, Simba, the ones that try to simulate the evolution of thousands of galaxies from the Big Bang to the present. They all include prescriptions for black hole growth and AGN feedback, and those prescriptions are typically calibrated to reproduce the local M-sigma relation. If that relation doesn't hold at high redshift, those calibrations might need to be revised. The simulations might need to allow for more aggressive early black hole growth, or different feedback efficiencies at early times, or seed masses that are larger than what was previously assumed. Several groups are already working on this, running new simulations with modified prescriptions to see if they can simultaneously match the JWST observations at high redshift and the local scaling relations at redshift 0. It's a delicate balancing act, because any change you make to the early universe has downstream consequences for everything that follows. And this connects to something even bigger, something that touches on the fundamental question of what drives structure formation in the universe. For decades, the standard picture has been that dark matter leads and everything else follows. Dark matter, halos form first, they merge and grow, and baryonic matter, gas, stars, black holes, falls into those halos and evolves within them. The galaxy is a passenger in a dark matter vehicle. But if black holes can form early and grow fast, if they can influence their host galaxies through feedback before the galaxy has really gotten going, then maybe the relationship is more of a partnership. Maybe in some cases, The black hole is the one setting the pace, shaping the gas distribution, determining when and where stars form. The question of who's driving, the dark matter halo, the black hole, or some combination, is one of the deepest questions in galaxy formation right now, and the answer might be different at different epochs. In the early universe, when everything is denser and more chaotic, the black hole might play an outsized role. Later, as the halo grows and the galaxy matures, dark matter gravity takes over, and the black hole becomes just one component among many. There's a metaphor I like for this, and it's not a perfect one, but it captures something true. Think of a city. In the very beginning, a city might grow up around a single institution, a fort, a cathedral, a trading post. That institution shapes everything about the early city, where the roads go, where people live, what the economy looks like. But as the city grows, as it absorbs surrounding settlements and develops new industries and builds infrastructure, the original institution becomes less and less dominant. It's still there, still important, but the city has taken on a life of its own. The modern city is shaped by geography, by economics, by transportation networks, by millions of individual decisions. The cathedral is still at the center, but it no longer determines the city's fate. Maybe black holes and galaxies work something like that. The black hole is the cathedral, foundational, influential in the early stages, but gradually becoming just one part of a much larger, more complex system. Now, there's one more piece of this puzzle that I think is worth spending a little time on, because it connects the M-sigma breakdown to something we haven't talked about much yet, and that's the role of gas. Specifically, the nature and behavior of gas in the very early universe, and how it differs from gas in galaxies today. Because when we talk about black hole growth and star formation and feedback, all of those processes ultimately depend on gas. How much there is, how it flows, how it cools, how it fragments. And the gas in the early universe was fundamentally different from what we see in galaxies today, and that difference matters more than you might expect. So let's talk about it. In the present-day universe, the gas inside a galaxy like the Milky Way is what astronomers call enriched. It's been through stars. It's been cooked inside stellar cores, blasted out in supernovae, mixed and recycled over billions of years. That means it contains a whole periodic table's worth of heavy elements: carbon, oxygen, silicon, iron, all the way up. And those heavy elements, even though they make up a tiny fraction of the gas by mass, have an outsized effect on how that gas behaves. They act as coolants. When gas contains metals, and in astronomy, anything heavier than helium counts as a metal, which is a quirky convention, but there it is. Those metal atoms and ions can radiate energy away very efficiently. They have lots of electron transitions available, lots of ways to emit photons and shed heat. So metal-enriched gas can cool quickly, fragment into small clumps, and form stars in a relatively orderly fashion. It can also settle into thin disks, develop spiral structure, and generally behave in the ways we associate with mature galaxies. But rewind to the first few 100 million years after the Big Bang, and the gas is pristine. It's almost entirely hydrogen and helium, with trace amounts of lithium and essentially nothing else. No carbon, no oxygen, no dust grains. And that changes everything about how the gas cools, how it collapses, and what kinds of objects it can form. Hydrogen and helium are terrible coolants compared to heavier elements. Atomic hydrogen can radiate, sure, but only through a limited set of transitions, and those transitions require relatively high temperatures to excite. You need gas above about 10,000 Kelvin before atomic hydrogen cooling really kicks in. Below that, in the absence of metals, the gas has very few ways to shed energy. The one exception, and this is important, is molecular hydrogen, H2. Two hydrogen atoms bonded together can vibrate and rotate, and those vibrational and rotational modes allow the molecule to emit infrared photons and cool the gas down to maybe a few hundred Kelvin. Not as cold as metal-enriched gas can get, but cold enough to allow gravitational collapse on large scales. Here's the thing, though. Molecular hydrogen is fragile. It's easily destroyed by ultraviolet radiation. And in the early universe, once the first stars and the first accreting black holes start lighting up, they flood their surroundings with ultraviolet photons that dissociate H2 molecules. So you get this complicated feedback loop. The first luminous objects create radiation that actually suppresses cooling in nearby gas clouds, which can prevent those clouds from forming stars. But at the same time, that same radiation might promote direct collapse of the gas into a massive black hole, because without efficient cooling, the gas can't fragment into small star-forming clumps. Instead, it stays as one big, hot, smoothly collapsing mass. And that's exactly the direct collapse scenario we talked about earlier, where you get a seed black hole of 10,000 or 100,000 solar masses forming in one dramatic event. So the chemistry of primordial gas isn't just a background detail. It's actually one of the key factors determining whether a given region of the early universe produces stars, or a massive black hole seed, or both, or neither. The balance between cooling and heating, between molecular hydrogen formation and destruction, between gravitational collapse and radiation pressure. All of that plays out differently depending on the local environment. Near a bright neighboring galaxy or quasar, the ultraviolet background might be strong enough to keep the gas from cooling. In more isolated regions, molecular hydrogen might survive long enough to enable star formation. The early universe was patchy, uneven, with different outcomes happening in different places depending on these local conditions. And there's another aspect of early gas that matters enormously, which is simply how much of it there was relative to everything else. In the early universe, galaxies were gas-rich to a degree that's hard to appreciate from our present-day perspective. Today, the Milky Way has converted most of its original gas supply into stars. The gas fraction, the fraction of a galaxy's ordinary matter that's still in gaseous form, is maybe 10 or 20% for a galaxy like ours. But at redshifts of 6, 7, 8, the gas fractions were probably 50, 60, maybe 80% or higher. These early galaxies were swimming in gas. Enormous reservoirs of fuel, just waiting to be funneled into star formation or into a central black hole. And the geometry of how that gas flows matters too. Modern simulations, and I'm thinking of work by groups using codes like FIRE and AREPO and the Renaissance simulations, show that in the early universe, gas didn't just gently drift into galaxies. It streamed in along filaments of the cosmic web in what are called cold flows or cold accretion streams. These are narrow channels of relatively dense, cool gas that penetrate deep into the dark matter halo without getting shock heated at the halo boundary. In the present-day universe, when gas falls into a massive galaxy's halo, it typically hits a virial shock, a boundary where the infalling gas slams into the hot gas already in the halo and heats up to millions of degrees. That hot gas then has to slowly cool before it can reach the galaxy and form stars. It's a bottleneck. But in the early universe, especially in lower mass halos, the gas densities along the filaments were high enough, and the cooling times short enough that the gas could stream right through without shocking. It could reach the center of the galaxy cold and dense, ready to form stars or feed a black hole almost immediately. Think about what that means for black hole growth. You've got a seed black hole sitting at the center of one of these early galaxies, and it's being fed by multiple cold streams of gas converging from different directions along the cosmic web. The accretion rate could be enormous, potentially super Eddington, as we discussed, because the gas is arriving so fast and so dense that radiation can get trapped in the flow. The black hole doesn't just grow steadily, it gorges. And because the gas is primordial or only lightly enriched, the cooling physics is different, the fragmentation is different, the feedback operates differently. The whole system is in a regime that simply doesn't exist in the modern universe. Now, you might be wondering, if all this gas is pouring in, why doesn't it all just form stars before the black hole can eat it? And that's a great question, and honestly, it's one of the things that simulations still struggle with. The answer seems to involve a combination of factors. Angular momentum is one. Gas that spirals inward has to lose angular momentum to actually reach the black hole. And that process involves complex dynamics like gravitational torques from asymmetric structures, bars, and mergers. Turbulence is another. The cold streams don't arrive smoothly. They're turbulent, chaotic, and that turbulence can both promote and suppress star formation depending on the scale. And feedback from the black hole itself plays a role, because even a modestly accreting black hole can heat and stir the gas in its vicinity, preventing some of it from collapsing into stars and redirecting it toward the accretion disk instead. What emerges from all of this is a picture of the early universe as a place where the rules were genuinely different. Not different physics. The laws of nature are the same, but different conditions, different regimes, different balances of the same forces. It's like how water behaves differently at different temperatures and pressures. The physics of water molecules doesn't change, but ice, liquid water, and steam behave in very different ways. The early universe was the same physics operating in a very different regime. Higher densities, higher gas fractions, lower metallicities, more vigorous accretion, more frequent mergers, stronger cold flows, weaker feedback. And in that regime, black holes could grow faster, galaxies could form stars more efficiently, and the relationship between the two could be very different from the neat, tidy M-sigma correlation we see today. And I think that's actually the deepest lesson from everything we've talked about tonight. The universe we see around us, the one with its orderly spiral galaxies and its well-behaved black holes and its neat correlations, is the end product of billions of years of evolution. It's the mature city with all its infrastructure and institutions and self-regulating systems. But the early universe was the frontier. It was messy, chaotic, fast-moving, and full of processes happening at rates and scales that we're only now beginning to appreciate. JWST hasn't broken our understanding of physics. What it's done is shown us that the universe's adolescence was wilder than we thought. The black holes grew faster. The galaxies matured sooner. The structures assembled more quickly. And the interplay between all these processes was more complex, more intertwined, more interesting than our models had predicted. There's something humbling about that, isn't there? We built these beautiful theoretical frameworks, lambda CDM cosmology, hierarchical structure formation, the Eddington limit, the M-sigma relation, and they work brilliantly for explaining the universe we see nearby. But when we push them back to the first billion years, to the very first galaxies and the very first black holes, we find that reality is richer than our models. Not wrong exactly, but incomplete. The universe had tricks up its sleeve that we hadn't anticipated. Direct collapse black holes, super Eddington accretion, cold flow feeding, primordial seeds, runaway mergers in dense protoclusters. All of these are ideas that existed in theory before JWST, but the telescope has given them urgency. It's turned them from interesting possibilities into necessary ingredients. And here's what I find most beautiful about all of this. We're living through the discovery. Right now, as you're lying here listening to this, there are astronomers analyzing JWST data, finding new high redshift quasars, measuring black hole masses in galaxies that formed when the universe was barely 300 million years old. There are theorists running new simulations with updated physics, trying to reproduce what JWST is seeing. There are graduate students writing dissertations on the M-sigma relation at high redshift, on the nature of little red dots, on the formation channels for massive black hole seeds. The story isn't finished. We're in the middle of it. And maybe that's the right note to end on. Not a conclusion, because this field doesn't have one yet, but a sense of where we are. We know that supermassive black holes existed astonishingly early. We know that their masses challenge simple growth models. We know that the galaxies around them were more mature, more structured, more massive than we expected. We have a handful of compelling ideas for how all of this happened. Heavy seeds, rapid accretion, mergers, favorable gas conditions. And we suspect the real answer involves all of them working together in different combinations in different environments. We know that the neat relationships we see in the local universe took time to emerge, and that the early universe was a more chaotic, more black hole-dominated place. And we know that we're just getting started with the data that will eventually sort all of this out. So as you drift off, if you're still with me, think about that for a moment. Somewhere out there, 13 billion light years away, there's a black hole that formed when the universe was younger than some of the mountains on Earth. It grew to 1 billion solar masses through processes we're still piecing together, in a galaxy that assembled itself faster than anyone thought possible, fed by streams of pristine gas flowing along filaments of dark matter in a universe that was smaller, denser, hotter, and stranger than the one we inhabit today. And the light from that black hole, from the superheated gas spiraling into it all those billions of years ago, traveled across the expanding universe, stretched from ultraviolet to infrared, dimmed to almost nothing, and was finally caught by a gold-plated mirror floating at a point in space 1 million miles from Earth. And someone looked at that light, measured it, and said, that's not what we expected. That's how science works. That's how understanding grows. Not in sudden revelations, but in quiet surprises, in data that doesn't quite fit, in models that need to be stretched and revised and sometimes rebuilt. The universe is patient. It's been holding these secrets for 13 billion years. And we're just now, in this generation, with these instruments, beginning to read them. There's something deeply peaceful about that, I think. The questions are vast, and the answers are coming slowly, and the universe will still be there tomorrow, still full of things we haven't figured out yet. And that's okay. That's more than okay. That's wonderful. Let that thought carry you into sleep. The universe is old and strange and more interesting than we knew, and we're learning, one photon at a time, how it all began.